Hey everyone, welcome to week 6, module 6. In this module, we're going to be covering the relationships between radii, chords, and tangent lines. But before we do that, let's review those vocabulary terms, which you can find at the top of this page and also in modules 4 and 5. Based on this visual, we can see that we have a tangent line, a radius, and a chord. Starting off with a tangent line is a line that touches a circle at exactly one point, which we could see right here. Not only does it touch a circle, but you're going to figure out in a couple of minutes that it's going to be perpendicular to a certain line that's within a circle as well. We also have a radius, and here we have our radius, which starts at the center of our circle and is extended to the outline of our circle, or we know radius as being half the length of a diameter. The last term we need to make sure we understand is a chord. So a chord is here in royal blue, and a chord is a line that connects two endpoints that are on a circle. Let's start by talking about the relationship between a radius and a tangent line. So we don't see a radius on here, and the reason for that is because we have 2 points, and when we connect those 2 points, we now have our radius. Here we have our tangent line. Whenever our radius and our tangent line intersect, it's intersecting at this point here, which is called our point of tangency. At this point of tangency, we're actually going to notice that we have a right angle, because the relationship between a radius and a tangent line is that the two lines are going to be perpendicular. So it doesn't matter if I was to move this radius over here and draw a tangent line, those two lines are still going to be perpendicular. And let's see an example of what this would look like. Here we can see no matter how much we move our radius, our tangent line stays with it, and it still continues to form that 90-degree angle. This can be summarized by the tangent theorem, which states that if a line is tangent to a circle, then the line is perpendicular to the radius of that circle drawn at that point of tangency. We've talked about the relationship between a radius and a tangent line. Now let's explore the relationship between a radius and a chord. We can see that we have our radius right here, so line segment AB, and we have our chord, line segment DG. We can also see in this example that our radius and our chord are perpendicular to one another because a 90-degree angle is formed. In this situation, we can also see that line DH and line HG are congruent to one another because they have the exact same length. So when we have a radius and a chord and the 90-degree angles form, meaning that the two lines are perpendicular, not only are they perpendicular, but AB, our radius, serves as a perpendicular bisector, meaning that it's cutting our chord in half. So again, bisect means to cut in half. This is in geometry, but also in life. So we know the lengths of each of these line segments. If we wanted to actually figure out how long DG was, we could just add these two values, or we could multiply it by 2, which means that DG is actually equal to 5.28 units, just in case you wanted to know. That concept is captured in the radius and chord theorem, which states that a radius that is perpendicular to a chord of a circle bisects the chord. And remember, perpendicular, you could see the symbol, which means 90-degree angle is formed, and bisect means to cut something in half. If you want to learn more about the converse of the radius and chord theorem, feel free to explore the MCPS video, which will be below this video. Now that we've learned about the relationships, let's actually apply some of these concepts to problems. In example 1, we're told that line AB is tangent to circle C at point B. So this is our point of tangency. If BC is 6 units right here, and AC is 10 right here, determine AB. So we see tangent, so let's use the tangent theorem, which states that our radius and our tangent line will be perpendicular, meaning we have a 90-degree angle right there. So now that I know that I have a 90-degree angle, I can see that I have the leg of one side. I have the other leg, this side, and we have our longest side, which is called our hypotenuse. So if we want to find this missing leg, we could use the Pythagorean theorem. So I'm going to plug this number in. So our first one is 6. We don't know our second leg. That's what we're solving for, AB. And our hypotenuse is 10. I'm going to skip forward to the answer. Feel free to pause the video if you want to try this yourself. Here you can see after doing all the work that solving for AB gave us a value of 8, say 8 units, and that would be our answer. Hope you got the same thing if you tried this on your own. Now let's go to our second and final example. Here we're told that line AD, which is right here, is the radius of circle A. And we're told that AD and BC are, remember this symbol means perpendicular, which means forms a 90-degree angle. We're also told that the length of BC is 5 units, so BC is this yellow line, so let me just write that in yellow. And we're also told that AC is 3 units, so this is 3 units. And we want to figure out how long these other side lengths are. We can do this. So we see a radius and we also see a chord, which means the radius and chord theorem would be perfect to use here because we also have a 90-degree angle. So since we have that, we should know that with the radius and chord theorem, it states that our radius serves as our perpendicular bisector in this case. So not only is it a 90-degree angle that we're getting, but we also have 2 line segments that are congruent to one another. So if we know that BC is 5 units, to get the length of each of these line segments, we're going to have to divide 5 by 2, which is going to give us 2.5 units. And that's our answer for the lengths of BE and CE. So 2.5 units and 2.5 units. All right, so let's go ahead and figure out how we can get line segment AD, which is this one, and line segment AB, which is this one. So we see that this is a radius, not because we're told that it's a radius, but because this line starts at the center of our circle and is connected to the outside. But we're also told that AD is a radius, which means that if this is 3, this also has to be 3. And looking here, we can also see that AB is a radius. So this is also 3 units. So in this case, all 3 of these line segments are 3 units. If I was to draw another one out here, that would be 3, which would make our diameter 6. That would be 3. The length of every single radius is the exact same. And hopefully you feel comfortable with these concepts and feel ready to practice. So there are a couple of examples after this. Feel free to work on those with the answer key at the end. Or if you feel like you're ready, go through the practice and the graded assignment, and you're done for the week. You got this, and good luck.